Okay, so we'll continue on in principal component analysis. Which we'll call PCA. And the idea is we project from m dimensions down to d dimensions, right? So the idea is, we can have a 3D object, a three-dimensional object that gets projected down to a shadow, which is a two-dimensional object, okay? Or in this case, we might have a 50-dimensional object, m is 50, and we project it down to 5 dimensions or something like that, okay? So we're going from m dimensions to d dimensions. And so what PCA does, PCA will define d vectors, okay? So we're projecting down to d dimensions, and those vectors, okay, w sub d, we're going from the first to the dth vector. Each vector is m dimensional. Okay, so if we're going from 50 dimensions, if our original data set has 50 columns and we want to project it down to 5 dimensions, we're going to define 5 vectors, and those 5 vectors will each have 50 values in it, okay? So each of these w sub d vectors represents a linear combination of the original m vectors. Okay, so for example, let's say you have your three-dimensional hand. I don't know how to draw a hand. All right, let's say you have a tube, right? Okay, so we've got some kind of tube here, and here I'm going to just draw the tube so that, let me redraw my axes here. Okay, I'm going to draw the tube so it is parallel. Okay, so one projection, so that we'll say this is x, and this direction is y, and this one is z. Okay, so one projection could look like this, right? This could be the shadow that, imagine just you got a paper towel tube or toilet paper tube, something. This could be one projection, right? And here we're going from 3 dimensions down to 2 dimensions, okay? The two here, we're going to create two vectors that represent a linear combination of X, Y, and Z. Okay? And according to this then, I'll call this PC1 and PC2. What is PC1? PC1 is equal, if we have X, Y, Z, this is just equal to 1, 0, 0, right? We've basically just projected down, and we've completely gotten rid of the information contained in Z, right? And PC2 would just be 0, 1, 0. Okay? So that's one possible projection, okay? Or you could, if we wanted to, if we just moved the quote the light around to change the way our shadow gets cast, the shadow that gets cast could look like this, right? And if this is the case, PC1 could be 1, 0, 0, and PC2 would be 0, 0, 1, right, for X, Y, and Z. So the Y dimension is lost there. Okay? Or you could imagine the light being moved somewhere else, and then you get a shadow that looks like this, right? And then now I don't know exactly what it's actually, so this shadow is filled in. And I don't know, if this is a solid, maybe it's not maybe it looks more like this or something. Okay, I don't know. Do these things make sense? And I don't, PC1 and PC2, I don't know what, some linear combination to get this, right? Just some combination of X, Y, and Z. So it looks like, whatever. Okay. Is that okay? So these represent, they are linear combinations of the original M vectors, but we're creating just two of them or something. Yes?
So are they like bases?
Well, in these ones, they ended up being bases. Well, I guess they could form new bases. Yeah. Okay. Yeah. Yes, they'll. Yeah, when you do I'm sorry. Yes, they could form a new basis because you'll get each principal component is going to be orthogonal to the other, and if you make them length 1, yeah. So. Okay, so does this week 8, Friday? It's already March, guys. So that's what we're doing. We're going from M down to D, and each D is a linear combination of the original M. Okay, so we will say the Dth element of the projection, so this will be X sub n and d, is going to be our vector W sub d times our original data, okay, for the nth observation. Okay, and what we want to do is we want to maximize the variance that we have in the resulting projected space. Okay. So after we make the projection, we want the resulting projection to have the most amount of variance. Okay. So it's kind of like if you're going to move the light around, you want to move the light in such a way that the resulting shadow is as, quote, big as possible, okay? Because we're hoping that will convey the most amount of information. Whereas it, depending on the object, right, you could move the light in such a way that the resulting shadow is as small as possible. But if you get a shadow that's as small as possible, you're going to kind of lose the most amount of information. So we want the biggest shadow that we can make, and the biggest shadow that we can make should be the one that kind of represents it will be the one with the most variation. It's like a loose interpretation, okay? Obviously, we're not always projecting down to two dimensions. So, and also each projected dimension is going to be orthogonal to all of the other projected dimensions, okay? Okay, so that means when you have Wi, the vector, so this is the projecting, kind of the weighting vector for the I out of the d dimensions. And if we multiply that by j, this is going to equal 0 for all pairs where I does not equal j. So they're all going to be orthogonal to each other, okay? And then we set a constraint so that the length of each vector is equal to 1. So that is Wi times Wi is equal to 1. Okay. So what we're going to do is we're going to do a little bit of a derivation here to kind of see how best to do this, okay? So we want to find kind of the set of W's that will maximize the variance in the resulting projections. That's what we want, okay? So what are the W's that we're going to pick, okay? So to kind of just make our lives easier, we're going to say that the original, we'll work with what we call the centered data. We will center the data so that the original dimensions will all have means of zeros, okay? To make the math easier, we will say we will work with centered data. That is to say that the means of the original data, the original, I guess, dimensions. So the column means are all 0. Okay, so that is So that is the mean of each y vector is 0 from n equals 1 to begin. All right, and so if the data is not centered, all we have to do is we just subtract the column mean from each column, right? Okay, and we'll okay, so we will start our PCA by finding our projection for the first dimension, okay? Or finding our projection onto the so basically, so what happens is for our first dimension is you're going to take the vector y sub n, project it onto your first dimension, and so it will return one value. Okay, so you have an observation y sub n. Okay, so this is in m dimensions. Okay, but if we're projecting it down to just one dimension, we have to turn those m dimensions into one scalar value. Okay, so you have an observation y sub n that gets projected down to one scalar value, okay, which is its value in the first principal component. Okay, and so that's going to be, we'll call that x sub n. Okay, so x sub n is just a scalar value, and this is just when you project y sub n onto onto w, it's going to turn into just one value x sub n. Or do you guys have questions, or yes?
So the projection is the first principal value.
Yes. So yeah, we're gonna just deal with our first principal component, right? So let's say we just want to go from 50 dimensions down to one dimension, okay? Or like in the heptathlon, we have 7 events, but we want to have just one scale to score, rank people from best to worst. So we're going to go from 7 down to 1, or 50 down to 1. Okay, so this will just be our first principal component. And this is going to be the one that captures the most amount of variation. Okay, and then the second principal component would be the one that's orthogonal to the first, and captures the most amount of variation of what remains. Okay, so we'll just start with the first example. Okay, so we just want to get from m dimensions down to, in our case, just one dimension for now. And what we want is we want to maximize the variance captured in this projected dimension space. Okay, so we want to maximize captured in this projection. Okay, and so the variance sigma squared is going to be 1 over n times the square root of x of n minus x bar squared, okay, from n equals 1 to big N. So far so good. So I'm going to just do a little bit of math derivation on the next few slides, okay? I gotta work a little bit quickly here. Okay, so we use the assumption that each of the column means are 0. So if we do, so x bar is going to be 1 over n times times this, right? Okay, and again x is this, so the kind of the mean of the x's, this is going to be just we can take this out of this because this is going to be a constant with respect to all the because it is a constant with respect to y. Okay, but we know this part becomes 0, so we have W transpose 0, so then we get, I guess the mean of x will be 0 itself. Okay, so our variance simplifies to sigma squared is 1 over n times x of n minus x bar squared, and this just becomes 1 over n times x of n minus 0 squared x of n squared. Okay, and so now I have okay, so we'll substitute this in right here to there. Let me just continue this onto the next slide here. Okay, so we have that in this expands to 1 over n. And so I'm going to go ahead and I'll pull out and just pull this out to the front. Okay, and this whole thing can be written as, so recall that y, the mean of all of these things is 0. So this can be written as 1 over n times the sum of y sub n minus y bar times y sub n minus y sub n transpose, okay? And this is the covariance matrix, right? So we get W transpose times the covariance matrix times this. Okay. All right. Okay, and we want to find the W's that maximize this quantity. Okay, so far we said the variance is this thing, and what we want to do is we want to find the vectors W that will maximize this quantity. Quantity subject to the constraint that W transpose W is equal to 1. All right, so how do we maximize something subject to a constraint? We can use a Lagrange multiplier, right? So to maximize subject to a constraint, don't worry if you guys forget it, okay? Subject to a constraint, we can use a Lagrange multiplier, right? And so we'll say L is equal to WCW minus a lambda times W transpose W minus 1, okay? And if we take this with respect to W, we'll get 2 times the covariance matrix times W minus lambda W equal to 0. All right, and now we have covariance times W is equal to lambda W. So we'll, so lambda is just some arbitrary constant, right? So I can divide lambda by 2 and just have another arbitrary constant lambda. Okay. Okay. Does this look familiar? No. Huh? What's that? So here I've got a matrix times a vector is equal to a constant times a vector, right? So we have a matrix times a vector is equal to a constant times a vector, all right? So basically W is an eigenvector of the matrix C. Okay, so do you guys recall eigenvectors? And did you guys watch that video that I posted at the very, very, very beginning of the quarter? And I said, watch this series on linear algebra. Okay, well, rewatch that series, or at least rewatch the one on eigenvectors, and refresh your memory. Okay? Yes, a question.
On the step where you did the partial derivative, clearly you see W minus lambda.
Probably. It doesn't matter. Okay, there's a constant here. It goes away. It's just a constant, right? It just, if I mess this up, it throws it off by a constant. Yeah. So W, the vector W is going to be an eigenvector of the matrix C, which is our kind of our variance covariance matrix of Y. And if you recall, what an eigenvector is you've got some square matrix A, right, which represents a transformation kind of in a-dimensional space. Yes, question.
What do you mean to say I can divide lambda by 2?
So here we got in the Lagrange, with Lagrange multipliers, right? You've got this thing that you want to kind of maximize, and you throw in the constraint here that has to be true.
Oh, is it like this combined step?
Huh?
Is that this?
And this is just some arbitrary constant lambda that doesn't really matter to us, okay? And so whether I multiply lambda by 2, it's just another constant lambda, okay? I mean, I could replace it with another letter.
It's just like a trick.
Yeah, just so I can leave it like this, okay? All right, and so just to kind of the eigenvector review is you got, some square matrix A, which goes from, M space to M space or D space to D space. If it's a square matrix, it doesn't change the dimension of the space, right? You multiply a vector by this thing. And basically, if you multiply A times a vector, and you'll get another vector. Right? So you might have some vector u, or let's say vector k, all right? And then when you multiply a times k, maybe it looks like this now, okay? After multiplication, okay? But for some of the vectors, you might have some vector u, where that when you multiply it by a, it ends up pointing in the same direction. So we've got some vector u, and this ends up just being not a times k, but a times u, just ends up being a scalar multiple of u itself, okay? So many times, most vectors will change directions after multiplication. Okay, but some vectors still point in the same direction. Okay, and if that's the case, then point in the same direction after multiplication. So this then u is an eigenvector of A. So if we look at the kind of the covariance matrix, the variance covariance matrix of Y, then its eigenvectors end up being the projections that we will use to kind of maximize the resulting variance for our principal components analysis. Okay. All right. So kind of to summarize, the solution of finding the projection of our data y onto a vector w okay, that maximizes the resulting variance of the projected data is to find the eigenvectors of our covariance matrix. Okay, so let's say you've got some data let's say it's normalized, okay? All right, so if we look at our kind of our covariance matrix, maybe we have something that looks like this. Maybe we get 1, 1, and 0.7, 0.7. Okay, and so here we have, data in 2 dimensions. Our matrix C is a square matrix that is 2 by 2. Okay, so if you have data in m dimensions, then matrix C will be a square matrix that is m by m, okay? And you will, if you ask for the eigenvectors of this, you'll end up with m different eigenvectors, right? Have a total of m eigenvectors, okay? But, you know, the first eigenvector will be the projection with the most variance. Okay, I got a couple minutes left. I guess I can do a quick demo that I don't even know if this will work in time, because I don't have any code pre-written up here. Okay, so we'll say library MVT norm, and then we'll ask for we'll say sigma matrix 1, 0.7, 0.7, 1. Will be R norm, RD norm. Let's do 100. Mean equals. Okay, so we have some data here, okay? So if I did covariance of y, this is what we get here, and then I can ask for eigen of this thing, and we would get these eigenvectors, and I can then call this $vectors, and we can try projecting $vectors times y, and this is projected onto this. There's my favorite. Let's see. Am I getting this the right way? I think I need to transform this way. Okay. All right, and we'll plot the projected data. Did that not work? Okay, let me. I think I did this. All right, so this is our original data. Let me see. I wonder why the vectors. Am I doing something wrong with my vectors? Y projected times $vectors. Okay. Something's getting kind of inverted here. I think it's fine. Okay. Let me just kind of, so this is this, and this is this, and you can kind of see it's basically, the signs on the eigenvectors are arbitrary, whether it's positive or negative. But you can kind of see a little bit of the structure here. So notice this one dot way out here, and then we kind of get like this triangle over here. If you kind of look at that, and if we compare this, that structure still exists, right? We have that one dot way out here, and then there's a triangle. It's just, this represents a rotation, because again, what a projection is it's a rotation of the object against how we're casting the shadow from the light. And so it's a rotation of this data such that the resulting projection in the first dimension will capture the most amount of variation. So let me just call V as this, and I'm going to just do -1 times our vectors, just so that the projection ends up being here. So here's our original data, and then after we project it, I don't know, maybe the rotation is easier to see. That we're going from, this is the original, and then after we project it, we're doing this. Huh? Yeah, this is the original, and we're just kind of rotating the data, okay? And that's what PCA effectively is. All we're doing is we're rotating the data in such a way that the resulting projection maximizes the variance that we see. In this case, we're projecting from 2 dimensions to 2 dimensions, so it's a pure rotation. But sometimes you might have higher dimensional, and you're projecting it down to lower dimensional, and we're doing the same thing, just now we're only seeing a shadow. Okay, we'll explore this a little bit more next week, so stay tuned for that, and we'll see you guys then.